Now we're going to go beyond the recursion that we've seen and bring back a new trick, or an old trick, in a new use. So we're going to take repetition and recursion, which we've seen has created it's created first addition, then multiplication, then exponents, then double up arrows, then triple up arrows, and we can see where that goes. But we're going to actually jump out of that and put in another kind of sort of fancy way to create a super fast growing function. So we already have some fast ones. We want to build on those, but in a little bit different way. Okay. So what I'm going to do is I'm going to list the numbers so far in a grid. So the rows here are the different functions, and then the columns are just what we can put into the functions. And just for simplicity, I'm always just going to use one of the numbers being 2. So 2 times, or 2 to the, or 2 double up. And we could certainly change those numbers as well, but that's not really the sort of the most interesting thing. Okay. So the summary table, the summary entry over here is just the formula for that function. This is 2n, this is 2 to the n, 2 double up n, 2 triple up n. And then we can imagine having 2, and then this notation means 2 and then k up arrows n. How's that defined? It's defined by repeatedly doing k minus 1 up arrows. How is that defined? Repeatedly do k minus 2 up arrows, and so on. Okay, and here's some of the values, 2, 4, 6, 8, 10, 2, 4, 8, 16, 32. Those are growing somewhat faster. Now these guys get impressive. 2, 4, 16, 65, 536, 2 to the 65, 536, and then 2 to that. That's the double ups. Those were pretty impressive for a while. The triple ups, 2, 4, 65, 536, then 2 double up 65, 536. Remember, that was the tower of 2s where we ended last time. And then if you went beyond that, you'd be doing repeated double ups. How many times? You'd be doing this many times. That's pretty hard to imagine. Okay, and if you want to think about that stuff and more, you can go to the ridiculously huge numbers video. Okay, but what was the cool thing we were able to do before when we put numbers in a grid like this to kind of jump out or create something that sort of qualitatively bigger? It was the diagonal method. Okay, we want a list that grows faster than any one of those rows that I just showed you, so we're going to take the diagonal. So now we're going to have a function where the first, you put 1 into it, you get this yellow square. You put 2 into it, you get this yellow square. You put 3 into it, you get this one, 4, etc. Actually, let's see. To make it match up, let's say 0, 1, 2, 3. Okay, so it's going to match with the number of arrows, perhaps. I think I've got, yeah, my diagonal's a little off here, but it's okay. It doesn't really matter. We just have a list where these yellow ones are the elements of the list. So let's see what that is. So the first on list 1, second on list 2, third on list 3, etc. And I think the way I highlighted the yellows, this doesn't quite match up, but it's the right idea. You take 2, just 1 up arrow 1, 2 to the 1 power, not big. 2 double up 2, 2 triple up 3, 2 quadruple up 4, 2 quintuple up 5. This guy, this function, you can think of it as just a list of numbers, a sequence, but a little more sophisticated term would be thinking of it as a function. That grows really, really, really fast. Okay? And in fact, it grows faster than any one particular entry on the list, because eventually you're using bigger and bigger functions. Does this grow faster than say the quadruple up arrow list? Well, the original ones actually are rather small compared to the things you get from quadruple up. But at this point, you're using quadruple up, and then you start using the bigger functions on the list that grow even faster, that were built out of successive repetition of quadruple up, etc. So it's going to grow faster than anything on any row on the list. It's very cool. It's a very simple idea, but it is the diagonal trick, really. Okay, so we need a name for this guy. Somehow it would come after all of list 1, list 2, list 3. If we want to rank them by sort of how fast they grow, this guy eventually grows faster than any of them. Okay, so the label should be some kind of infinity. But this is really an ordinal infinity, because it really is important that we're interested in it, not because it's a bag of stuff that's bigger in an unordered fashion. It really came after it by a process that was fundamentally ordered. So this is going to be, the label for this list is going to be ordinal infinity. Turns out omega, lowercase omega, is the terminology going back to Cantor himself. And it's the standard name for organizing an infinite process of the simplest kind. It's essentially the ordinal version of Aleph naught, just the simplest kind of infinity, but it's really looking at it in a different way. Okay, so right now we just have this, the use we have for omega is that we wanted a label for a list that didn't show up on our master list of lists, and it really should come afterwards. So this is the new function that's going to grow super fast, and it's kind of abbreviation for jumping out of that loop of recursion and creating something big in a new way. But the really cool thing is we're not even done yet. We don't just say, oh, we've diagonalized, that's about it. Well, that wasn't where we finished with the cardinal story either. There's a list omega plus 1 as well. Let me tell you about the list omega plus 1. And so this is where we start to discover that there's actually some kind of arithmetic we can do with infinite numbers. And ordinal arithmetic is a very cool subject. I'm going to give you the tiniest introduction to it. Okay, so remember, the thing we're doing is we're still creating functions that create huge finite numbers. And the role for the infinite things is really as the labels of the lists, the labels of the functions. And that's how I'm going to kind of leave it usually. So how is omega plus 1 useful? What does that mean? Okay. Well, let's go back to the old version of creating a new list. Let's repeat the operation on the old list. Okay. So here's the deal. Okay, remember that I'm going to review just one more time how we created things in the normal way, going from one row to the next. So 2 to the third equals 8. Why was that so? Okay. It was excuse me. It was repeat the operation on the old list in a certain way. So first we just look at the first entry and we get 2. We take the output and we look at that entry on the list. We recycle the output into the input slot of the function. And in terms of thinking of them as just lists of numbers, it means take this number, what was the output of the arithmetic operation, and then say, okay, I'm going to look at that position on the list. So that means look at this guy. Now I do that again. Oh, 4. What do? I put that in as the input of the function, or in other words, I look at the fourth element in that list, and I get 8. How do I know when to stop? It's the 3 controls just how many times do I do that process here. So I've highlighted 3 things in this row, and I get 2 to the 3 equals 8. So I started it out with 2 times 1 is 2. Then I put the 2 into this slot. Then I put the 2 into this slot. That meant I had to go to position 4 in that list. Okay. So now I want to try to show you that with the list omega plus 1, or the omega plus 1th function in this cool hierarchy of fast-growing functions. So we start with the first item on the previous list, which is list omega. But the definition of list omega was that was the first item on list 1, and that's just 2. Okay, so I've highlighted the yellows again because that's list omega that we're going to use here to create list omega plus 1. The start of it all is I just plug in to the first one and I get 2. Okay, now remember I wanted to get the fourth item, so I'm going to do this 4 times. Now the output of the function omega, the diagonal, the yellow ones, was 2, the first output. That tells me which item to look at on list omega, the yellow list. Okay, by definition, that's the second item on list 2, which is 4. Let me show you. Okay, so we started here, we took the output, and that told us how far down the diagonal to search. Okay, just to 2, that's fine. Now the output of that is 4. Now that's going to tell me, okay, I need to go 1, 2, 3, 4 down this diagonal list. Ooh, that's getting big. Okay. So here's the summary of that. Okay, so since that output was 4, we next find the fourth item on list omega, which by definition is just the fourth item on list 4. That's the diagonal idea, which is this really big number. Okay, so that's this guy. All right, we're not quite done yet, though. We've done 1, 2, 3. Then the fourth thing would be the answer to our question, the fourth item on list omega plus 1. Okay. So we're almost done. So now we take this unbelievably huge number, 2 double up 65,536, this huge string of powers of 2. We look at that item on list omega, which remember was an incredibly fast-growing list of numbers. It's the hugest item on list huge, and that's really, really, really big. Okay, so we're going to take back. Let me take back to this thing. We started here. We let the 2 tell us which item on the list to go to. We let the 4 tell us which item on the list to go to. And then we let this huge number, we say we search that far down this yellow list. And we already know that this yellow list is unbelievably fast growing. And we're told to put in a super huge number in terms of which item on the list we look at. And remember what we just did. All we looked for, we put in the number 4 into this cool function omega plus 1. It's really, really big. Okay. So I want to give you a little picture of what does it mean. We've got the tiniest taste of this idea of an infinite ordinal number. We've got two examples so far, omega and omega plus 1. And I just want to give you a visual picture. There's actually a pretty simple visual picture of this. Okay. So first of all, I want to just give you a picture of the number 4 as an ordinal number. It's just a stack of stars, 4 objects in line. Okay. And our order is going to be going up and to the right, just because for some reason I picture it that way. Okay. Omega, what do you want to picture omega as? Well, omega, the way we started to need it was we needed a label that went in an ordered sequence. It was the thing that would go after every natural number. When we've thought about 0, 1, 2, 3, 4, etc., we needed something that actually had a place after every single one. And we called that omega. So I'm going to visualize that by an arrow here. And so omega is sort of the limit of all finite numbers as finite numbers go off to infinity. Okay, that's what this lim n notation is going to be. It's just let the number n go off to infinity. Okay, and limit just basically means put something new after all the things in the list. So I want to look at ordinal arithmetic a tiny bit. I've claimed to you that omega plus 1 is a good name for the label that we would attach to this immensely fast-growing function that I was just talking about. Okay, well, what about 1 plus omega? Is that the same thing? Usually it would be the same thing as omega plus 1. Turns out it's not. This is the funky thing about ordinal addition, is that it's not a commutative operation. Plus, in ordinal arithmetic, just means put one ordered list and then put the next ordered list right after it. Okay, and then you can rearrange it visually as long as you're not actually reordering anything. So 1, you just have 1 star, and then nothing else vertically. And then you start over, and then you have another star, 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 star. Okay, and then, boom, the arrow going off to symbolize that I've put one thing after every one of those stars. Well, you know what? If I just slide this guy right down here, it's the same thing as omega. It's just 5 stars in a row, and then an arrow going off. So in fact, 1 plus omega is the same thing as omega. I just stuttered when I started the list, but that doesn't really change the fundamental nature of the list. On the other hand, omega plus 1 is really a very distinct label. That is, start with a finite process, then do something to jump out of the loop, something that deserves to go after every single one of the finite ones. That's, in our example of the creating lists, the creating huge growing functions, going from one star to the next was the recursion process, and then the arrow was the label for the diagonal process. And then we started the recursion process over again. But this is very, very different from omega or from 1 plus omega. I can't take this star and kind of put it on top of the arrow. The whole nature of the arrow is it just goes off to infinity. So if I have 1, 2, 3, 4, 5, dot, 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 and the dot, dot, dots are supposed to symbolize, hey, do something new, and then start over with a new single element, that's really quite different. Similarly, I could have omega times 2. Star, 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 then diagonalize, and then start the recursion process over again. So for example, this could be a way to create even faster growing functions. Create the list omega plus 1. Not that hard to create a list omega plus 2 based on repeatedly doing omega plus 1. Then omega plus 3, then omega plus 4. Build a new list of lists or a new table of functions, and diagonalize on that guy. Okay, this is going to be a symbolism for the how we did that. We did a certain number of recursions starting with successor and addition and multiplication and exponentiation, etc. And we did one diagonalization step. Then we started the recursion, the ordinary recursion process over again, did that over and over and over again, and then we diagonalized on that. If we want it formally, omega 2 is supposed to be the limit of take omega, which is this stuff with this red arrow, plus 1, and then plus 2, and then plus 3, and then plus 4, and then say, well, what if you just kept doing that? Omega squared even makes sense. That if you take omega, and then another omega next to it, add it to it, add it to it, add it to it, add it to it, and then just do it infinitely in this direction as well. So this is kind of a picture of what omega squared would mean. Remember, there's various uses for ordinals. The way I would like you to encourage you to think about ordinals in a very concrete way. It's just a shorthand for here's a scheme for creating one of those incredibly fast-growing functions. You start with successor and then do recursive definition and diagonalize. Start with and then just do recursive definition again and again, diagonalize. Recursive definition again and again, diagonalize. See if you can see the pattern in that, and then take the limit of that and do that arbitrarily many times. Okay. So basically, why stop at omega or at omega plus 1? We can create omega plus 2, omega plus 3, omega plus 4, etc. We can diagonalize again to get omega 2, omega times 2. Notice 2 times omega. I forgot to put that up on a slide, but that's the same thing as omega. That would be if you had, instead of this thing, if you had the dots like 2 dots, or 2 stars on top of each other, then 2 stars, then 2 stars, then 2 stars, then 2 stars. You can restack those so that they just are one infinite list of stars. Once you've got omega 2, you can add 1 to that, and add 2 to that, and add 3 to that. We just have these 2 fundamental processes for creating new, interesting, fast-growing functions. One is recurse. Do the recursive version, say repeat the previous operation a certain number of times. That corresponds to adding 1 to our ordinal number, which keeps track of the pattern. And then there's the diagonalization step, which corresponds to what these dots are hiding. So you can diagonalize again. You can get omega times 3, omega times 4. Turns out to make sense to have omega squared, omega cubed, omega to the omega, omega to the omega to the omega. Gets a bit complicated to talk about that in detail, but it's the same idea of it's all built out of adding 1 and taking limits and sort of wrapping up a whole list and saying, oh, I can summarize this whole list by a new ordinal number. It keeps going. So that's led us into some pretty abstruse territory. And I wanted to, as I said, I wanted to ground it by thinking of ordinal numbers for our purposes as just labels for different styles of recursion. Remember, that's what I said at the start when I started introducing ordinals, is that one way to think about them is that they're just different ways to describe all the different patterns of how you could do recursion. And in our case, it's particularly for the goal of creating fast-growing functions with finite numbers. Well, ordinal arithmetic, though, is a subject in and of itself. And the classification of ordinals is really quite a hairy business. There's a lot of different infinite ordinals. One of the interesting things about all the ordinals that I've talked about so far, if you use the cardinal method to compare them and forget about the order, let's look at a picture, for example. Let's look at this guy. From the ordinal point of view, it's really important that you step through this way. 1, 2, 3, 4, da 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 da, and then start over. 1, 2, 3, 4, da da da, start over. That is, there's a certain order here. So, for example, this star goes after all of the stars would be in this column. This star goes after all of these guys. But remember, from the cardinal method, that doesn't matter. You're supposed to ignore any kind of order, any kind of structure. Just think of it as an unstructured bag of objects, a set. From that point of view, this is just something I could zigzag. If I reordered them as I wanted to, I could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I can use the zigzag trick to show that from a cardinal perspective, this is just the ordinary kind of infinity. We haven't actually gone past Aleph naught in terms of cardinal comparisons. Ordinal comparisons are much, much more finicky, and they say they can tell the difference between a lot of different patterns of order, where if you forget that order and that structure, a cardinal comparison would say, these aren't interesting yet. They're all countable. So all the ordinals that I've talked about so far, all the things on this list, even this thing that from an ordinal perspective is an immensely huge ordinal number, from a cardinal perspective, it's just Aleph naught. Okay? But there's another way to combine ordinals and cardinals, which is more interesting, rather than just saying, let's look at ordinals and then forget why we were interested in them in the first place as patterns of recursion or patterns of order. What we can do is we can use them to label the cardinals. So remember, we had started creating these different cardinals, and there were definitely some issues, like the continuum hypothesis, about exactly what does Aleph 1 mean, how does it relate to various other things we're familiar with. But we have this sequence of alephs, and it turns out you can order them in exactly the way that ordinals should be ordered. And it turns out you can talk about, for example, aleph sub omega. So the infiniteth infinity, where the thing, the index, the thing that's keeping the infinity straight, is very much about order, but the actual infinity we're talking about is just about an unordered bag of stuff. I think that's super cool how these are combining. You can talk about the omega plus first aleph. You can talk about the omega to the omegeth aleph number. So to even think about this, you really have to have a certain mastery of both what the ordinals mean, because that tells you how these guys are ranking, and what the alephs mean, which tells you how you know that this guy's bigger than this guy, is bigger than this guy, etc. So remember that to create a new aleph, you really are getting much bigger. You're using the diagonalization trick that we did in an earlier video to create a vastly bigger kind of infinity. Much more different than the difference between the ordinal ones that I was just talking about. And yet, how many times did I have to do that? Omega to the omega, that's a big ordinal number. I had to create new aleph numbers many, many times in very clever fashion to create something that is this big. And it doesn't even stop there.